transform, and now we'll do the Z transform. So basically, Fourier and Laplace, we are more into continuous time signals. Now, with the Z transform, we'll focus on discrete time signals. So in continuous times, we have h of t, and we do transformation either Fourier or Laplace to get either h of e to the power j omega or h of s. That's in the continuous domain. Now in discrete, we have h of n. And in there we have a transform called the Z transform. We will have h of z. And you'll find like a lot of things are similar between like all transforms. In here, we do integrations because we have continuous time signals. In discrete time, we have summation. So integration, we know how to apply integration, like you have an exponent, and you can use integration by parts, by substitution, etc. And here in the summation, we will refer to the tables at some point, but also we will provide a table for the summations itself. So it's not like the Z transform pairs, and we will rely on them actually. All right, so here is the objective of this lecture: to analyze systems described by differential equations. We'll do that also like y prime of n and so on, pretty much like what we did in the Fourier and Laplace. Okay, so we need to represent everything in the Z domain. So the Z transform is a discrete time concept of Laplace transform. Again, it's pretty much the same concept, time domain or discrete domain into frequency domain. So the transform is given by this expression, summation from n equal negative infinity to infinity. So we basically do the summation of all points in discrete time. And that's why they call it bilateral transformation, because I have both ends of the domain, the discrete domain, from negative infinity to infinity. So that's why they call it the bilateral Z transform. H of n, z to the power negative n. Even though like the summation looks some point not conventional like in integration, but the easiest way you do is like substitute values of n and you just apply the summation. All right, so basically z is a complex variable. If you want to relate it to polar coordinates, z equal r e to the power j omega. And this is how we relate it actually to the Fourier transform. Okay, let's see. So that's it about this slide. There we go here. So expressing the complex variable z in the polar form. And then here, since we have the exponent, so we have the magnitude, and this is the phase part. So this one, since it's a complex number, it has the real part and the imaginary part. The real part is r cosine omega, and the imaginary part r sine omega. It's just basically applying the Euler identity for this exponent. Okay, so usually we are not, let's say, doing this, like do the substitution of z into r e to the power j omega. It's just to show you that the Z transform is basically a Fourier transform when you apply this or substitute this expression. So we can observe that x of z equal x of r e to the power j omega is a Fourier transform of this expression. So basically your input signal x of n is weighted by r to the negative n, then you apply the Fourier transform for that expression. So for this transformation to hold, basically to converge, it will not go to infinity. So the Z transform, we require that the Fourier transform of this one also to converge. We will not use this concept. We'll just focus on the Z transform and see where is the region of convergence. The region of convergence is basically the values where the transformation exists. We've done this concept last week in Laplace transform. And in here, we're going to do the same. All right, so the Z transform of a sequence has a range of values of Z where X of Z converges. So this is the region of convergence. Now there is a concept here, the unit circle. Basically in Laplace, we have done in the S-plane. So we have S, and this is what we call the S-plane. And so this is the negative half, this is the positive half. So that's in the Laplace domain. However, in the Z domain, we don't deal with something like this. We have the coordinates. So that's the real axis, imaginary axis. And we have this circle here. So let's assume this is a circle. So this is what we call a unit circle. So the value here is 1. This one is j omega. This is also 1. And this is also 1. So that's just basically a circle with a radius 1. All right, so it says here, if the region of convergence includes the unit circle, let's say, for example, my region of convergence is something like this, and it's inside, then we can say the Fourier transform, the Z transform converges, and also the Fourier transform converges. So let's take this one as an example. X of n equal a to the power n u of n. So I'll take it to the whiteboard. Okay. Okay. Duplicate. Okay, so I'll open the whiteboard. So x of n equal a to the power n u of n. Find x of z. Now, when you are required to find x of z, intuitively you should know also you need to find the region of convergence for this expression. So even if I don't ask about what the region of convergence is, you need to find it right after you do the z transform. All right, so x of z by definition equals summation from n equal negative infinity to infinity x of n z to the power negative n. So we just substitute negative infinity to infinity x of n, this expression here. So I have a to the power n u of n z to the negative n. Now we know the unit step function. So this is n, and the unit step function, it just pulses with an amplitude 1 and starts from 0, 1, 2. At negative points in time, it's 0. Okay, here also 3. So all the way to infinity. And from negative infinity to 0, I have 0 values. So basically, the job of this unit step function is to change the limits of this summation. Since I know that from minus infinity to 0, I have no values, then my summation will be from 0 to infinity a of n z to the negative n. Are we clear about this concept? Any questions about this? Like the unit step function has only values at positive points in n or in time, let's say. So for negative values, there are zeros. So when you multiply these expressions here with this unit step function, and you want to apply the summation, I know that I have the summation from minus infinity to infinity. However, I know that from minus infinity to 0, I have no values because the unit step function is zeros. So here, basically, I'm summing, let's say 0, 0, 0, 0. Then I'll start having values after this point. So the limits of this summation gonna change from negative infinity to infinity and to 0 to infinity. All right, so we know that z to the negative n equal 1 over z to the power n. So we can have it this way, summation 0 to infinity, a to the power n, z to the power n, and we can take the power as a common factor, or not a common factor, it just we can simplify the expression like this. Now, a over z to the power n. Now, for this one, we cannot find it, let's say, numerically. We need to apply the expressions, the tables. So let's check here, and we have this table. This table will be provided during the exam. All right, so from the given expressions there, which one is related to this expression? So I have the limits from 0 to infinity. So I'll go to the table. I will look for the one that has limits from 0 to infinity. So I have this one, 0 to n. So it's not the same. I have 0 to infinity. Now I will look at the expression a to the power k. And here I have a over z to the power n. So basically, this is the summation. This one is similar. There I have a is related a over z. So basically, this expression could be evaluated using this summation. Okay. Again, most important part, 0 to infinity. Now, don't be confused. This is one is k, and I have the power k. And there, my summation is at n. So it is the same as I having it to the power n. It's just an index. It's just a variable. So then, by using the tables, n equals 0 to infinity, a over z to the power n should equal, go to the tables, 1 over 1 minus z. 1 over 1, sorry, not no, 1a. Oh, minus a. Exactly. Now, there is a condition. Now, if you look at this expression, what is the condition for this summation to be, let's say, summable? Like I can apply the summation. A over z, absolute value, should be less than 1. Think about it. We are raising this expression into powers. Let's say we start at n equals 0, then n equal 1. So basically, a over z to the power 0. Or let me just simplify it somewhere to the side. Now I have n equals 0 to infinity, a over z to the power n. That equals, we start at 0, a over z to the power 0, plus a over z to the power 1, just summation, plus a over z to the power 2, plus all the way to a to the power infinity over z to the power infinity, right? All right. Now, let's imagine that a over z is larger than 1. Let's assume that one. Let's call it that's 2. Any value larger than 1. It's going to be 2. So I will have 2 to the power 0 plus 2 to the power 1 plus 2 squared all the way 2 to the power infinity. In this case, the value what will be? The answer will be infinity. So in this case, it will diverge. Now, what is the opposite of converge? Is diverge. Converge, the summation will lead to a value. It will, let's say, keep descending until it demolishes. It becomes 0. That's summation. Now, if this value goes to infinity, then we call it diverge. The function will kind of burst, just go to infinity, which is not desired. However, let's assume a over z less than 1, like in this case, 0.5, for example. So in the other case, 0.5 to the power 0 plus 0.5 to the power 1 plus 0.5 to the power 2, 0.5 to the power infinity. So in this case, it's going to be 1 plus 0.5 plus 0.5 squared is how much? 0.25. So you notice that the number keeps going, let's say, down. In this case, 1 over 0.5 to the power infinity, which is basically 1 over 2 to the power infinity. 1 over 2 to the power infinity. That's going to become a 0. So in this case, it converges. So for this summation to hold, this condition should be maintained. And this is the concept of region of convergence. That's what we did in Laplace transform. Like in last week, we ended up doing the integration. And we wanted to make sure this integration, the results of the integration will not go to infinity. So we applied a certain condition and we found a region of convergence. And this is exactly the same. So here, the region of convergence, A should be less than Z, or Z should be larger than A. And we maintain the absolute values. You just like do cross products here, A less than Z or or Z larger than A. So if you want to apply it into the unit circle, so I have my unit circle here. This is 1, and A could be any value here. So this is A. So we draw a circle with a radius A. And we said Z should be larger than A. So that's the region of convergence. Okay, we can go back to the slides and visit the same concept. We're just going to repeat what I just said. Okay, let's duplicate. All right, so we have it here. The unit step function, change the limit. I have this one. Then this is what we ended up with. Then we substituted this expression into finding this value 1 over 1 minus A over Z. And you can simplify even more by multiplying by Z on top and at the denominator and denominator. So in this case, you will have Z over Z minus A. All right, so here's the condition. That's from the tables, and the absolute value of R should be less than 1. And this is what we had from before. There you go, that's the one. All right, so let's go back into the region of convergence concept. So the Z transform of a sequence has a range of values of Z where X of Z converges. If the region of convergence includes the unit circle, then the Fourier transform also converges. So that's just another condition to like relate Fourier transform into the Z transform. Okay, so the region of convergence is just a ring in the Z plane centered about the origin. And that's what we just did before. So that was the region of convergence. It's just a ring centered at the origin. And here's my region of convergence. Another property here that the region of convergence does not contain any poles, and you know what the poles are, or the concept of poles is basically the zeros of the denominator, and they are very important to determine stability. So if x of n is a finite duration, then the region of convergence is going to be the entire z plane. Basically, if h of n or x of n, sorry, is just a sequence like this, 1, 5, 10. And if I ask you what is the region of convergence of this, it's going to be the entire Z plane. Just one of the properties here. All right. So here are the geometric series that we're going to be doing for this lecture. Another example, x of n equal negative a to the power n u of negative n minus 1. So we'll take it also to the whiteboard, solve it from scratch. X of n equal negative a to the power n u of negative n minus 1. Let's double check. Yeah. All right. Before applying this summation and everything, let's try to understand this unit step function. How to do it. First of all, we know that there is a time reversal because I have negative n. So my unit step function is going to be something like this. And we have zeros at these points. And the amplitude is 1 for all. Now, what will be this point? The easiest way to find this value is basically the zero for this expression. So I have negative n minus 1 equals 0. Because if you remember, the unit step function u of n was something like this. And starts from 0, 1, 2, and so on. And this one is the same. It's a unit step function. My first sample will start at this point when it's equal to 0. All right, so let's move this one here. So n equal negative 1. And that's it. So this is negative 1, negative 2, negative 3, negative 4. So this is 0, 1, 2, 3, and so on. So that's my expression for u of negative n minus 1. Is it clear how we obtain this? Basically, the unit step function, just know there is a time reversal or it's going to be a standard one. Now, what will be the first sample? Just look at the 0 for this expression, and you'll find the sample immediately there. All right, so my summation now, x of z equal summation n equal negative infinity to infinity, negative a to the power n, u of negative n minus 1, z to the power negative n. This one a to the power n or negative n. n. Now we see that what will be the job of this unit step function? We say this is going to change the limits. Now, what will be my new limits? So I have the summation negative a to the power n, z negative n. What will be the limits? Just look here. Where do I have values for this expression? Where, like that's going to be at the beginning or the end? Okay, if it's the beginning, that means I'm taking these values, right? And my summation will become what? 0. I have to consider only this interval. From negative 1 to infinity, I'm getting zeros. So it will not do the summation. So what will be my limits? It's going to be from negative infinity to negative 1. Is it clear? Again, the task of the unit step function is to find you the limits of the summation. In this case, I have the unit step function. It has values from negative infinity to negative 1. From 0 to infinity, there are no values. So I will exclude that part. So here's going to be my limits of this integration. Okay, one important property here, or let's take this one outside. So I have negative infinity to negative 1, a to the power, and it's going to be the same as the previous one, a to the power a over z to the power n. Now, if you go to the tables in the previous slides here, there is no such summation from negative infinity to negative 1. But we have from a constant to infinity. So this could be a candidate to work on. One important property is you have summation from A to B, whatever expression here, that's going to be equal negative summation from B to A. And you have it like this. So basically, you just reverse, when you reverse the limits of the summation, you reverse the sign of the summation. That's just the trick of solving this question. Let's confirm here if they are using the property. All right. And there you go. So from negative infinity to negative 1, it's going to be 1 to infinity. Sorry, the negation is not on the side. It's going to be on this side. You do not negate the expression, you negate the power. Yeah, apologies for this. So let me fix it there also. Okay, let's do the eraser. So when you have something to the power n, It's going to be the same thing, negative n. That's the only change happens there. So in this case, I'm having this summation. And negative infinity to negative 1 to the power, okay, n. Okay, I did not reverse the expression here. Let me just redo it. This is gonna equal summation from, oh, okay, my bad. This was just, okay. So this one is fine. I just took the sign outside the summation, negative infinity to negative 1, same expression. That's gonna equal the negative sign still there, summation from 1 to infinity, a over z. Now it's going to be to the negative n. All right, now a over z to the negative n is basically 1 to infinity z over a to the power n, right? Just when you flip or take the reciprocal, that's you're raising it to a negative power, negative and negative will change. Now, I think we can find this expression from the tables. So I have a to the power k equal a to the power n 1 minus r. So I have this expression, I have n here. So that's my n in this case equal 1. When you want to relate n equal 1. So in this case, I will have 1. Let's go back to the table. A to the power n. A is basically z over a to the power 1. That's n over 1 minus z over a to the power, go back to the table, just there's no power there. So in this case, the expression will become z over a over 1 minus z over a. And just multiply a and a, you will get z over a minus z. And that's the answer in this case. Let's go back here, check the slides. So z over z over a minus 1, you multiply by a, and there's a negative sign. Yeah, here you have the negative sign, so you multiply by negative here. All right, so let's check here. Let's go over the steps. So as we said, the task for this unit step function will change the limits of the summation from negative infinity to negative 1. So here is my expression. And there you go, reverse the limits of the summation. So it's going to be from 1 to infinity. And you have negative n, a over z. Okay, then we have it here, negative. That's from the beginning. This has been always there, so let's not forget it. In this slide, they solve it differently. So they partition the summation to start from 0 to apply this expression, but this one also will lead to the same answer. Okay. So it's going to be from 0 to infinity minus this first element. Finishing this, and you will get the exact same expression. So in this case, if you want to simplify it, z over z over a minus 1 multiplied by a over a, you will have z over z minus 1 minus a, sorry, z over z minus a. And I believe that's what we got here. Here it's negative z over a minus z, which is basically you can have it z over negative a minus z, and it's going to be z over z minus a. And it's the same expression. All right, now what about the region of convergence for this expression? As I mentioned, the region of convergence, what values of this expression will make the summation summable. Basically, you will have Z over A absolute value should be less than 1. So Z less than A. So the region of convergence, if you want to apply it in the unit circle. So here, let's assume this is A. This is the value A. So Z minus A, that is the region of convergence for this expression. Are we clear about the region of convergence? All right, so let's see. And compared to the previous example, I believe we got a similar expression, but with different region of convergence. Okay, let's go back to the slides. Current slide. Okay. Continuation of the solution, and here is the region of convergence. That's the real axis, so that's where A is, and that's the region of convergence for this function. Another example here, given a signal x of n, find the z transform x of z and its region of convergence. We did not do the tables yet, but we'll try it with and without the tables. So in this case, you have basically two functions. You can consider this one as x1 of n, and this is x2 of n. So x of z equals x1 of z plus x2 of z. So let's apply the transformation here. Actually, we don't even have to do it because we already found a to the power n u of n, and both of them are of the same thing, right? So let me check what was the answer. I forgot. It was the first problem, right? Yeah, a to the power n u of n. So the solution was 1 over 1 minus a over z. So 1 over 1 minus a over z, or it's going to be z over z minus a. In this case, for the first example, I have 7 times z over z minus 1 over 3 plus 6 times z over z minus 1 over 2. Like it's basically the first example, but with different values of a. Now, what will be the region of convergence? So the first one here, the region of convergence was absolute value of z larger than 1/2. And this one, the region of convergence, 1 over 3. Convergence equals absolute value of z larger than 1 over 2. Again, referring to the first example, the region of convergence, absolute value of z should be larger than a. And in here, I have 1 over 3 for the first expression and 1 over 2 for the second expression. Now, like the Laplace, the region of convergence will be the region of convergence of x1 intersected with the region of convergence of x2. So if you want to do it at the number line, my first expression is at 1 over 3. And 1 over 2 is going to be here. So the first one, the region of convergence, like all these values. And the second one, the region of convergence is all these values. So the region of convergence will be what? Z larger than 1 over 2. Clear? Or if you want to do it as the unit circle concept, so this is at 1 over 3 and the other one as 1 over 2. So let's draw with different colors. So the first one, this is the region of convergence, 1 over 3. And the second one, 1 over 2. So basically the intersection is going to be this outer region. This one is not included. So the region of convergence should be at z larger 1 over 2. All right. So here is the detailed solution, but we refer to the previous example to save time. Okay. All right. Now, since we have the transformation there, like here. Now, if you were asked, determine whether this signal is stable. Now, to find stability, you look for the poles. Then the poles should be inside, any idea? The unit circle. So basically you draw at the Z plane. And if the poles, we symbolize them by X's. If they are somewhere inside the unit circle, then it is stable. If they are outside the unit stable, the unit circle, then it is not stable. So to find the poles for this expression, we need to simplify it. Basically, I will do a cross product. And we will have the expression like this. So I have uh, 6z this times z minus 1 over 3 plus 7z times z minus 1 over 2 over z minus 1 over 3 z minus 1 over 2. So the determined stability poles are the zeros of the denominator. So I have two poles. The first pole equals 1 over 3. The second pole equals 1 over 2. So if we go to the unit circle, so I have the first pole 1 over 3, second pole 1 over 2. So in this case, we can make the comment that the system is stable. So I'll go back to the slides, and this is the idea for this expression here. We don't have to worry about the zeros because they are not related to the stability of the function. Question? No, in Laplace, that has to be left to the S-plane. So there is no unit circle concept in Laplace. Okay, so here, like just after simplifying, we don't need to worry about the zeros, but if you were asked to find the zeros, just simplify this two expressions here, then find the zeros.
It's exactly.
Find the zeros and the poles of the Z transform. And did you talk about stability? No. Yeah, just where to find them. And in MATLAB, there's a command for that. I think Z-plane or something. And in the lab, did you take Z transform or no? Okay, probably introduce it in the future. But yeah, so when you find the zeros and the poles, again, the concept of poles is all about stability. Stability. Yeah. Just a quadratic or cubic expression. Then find the zeros of that expression. If you find for the numerator, we call it zeros. For the denominator, we call it poles. And once you find the poles, you locate them at the z-plane. Or basically, if they are less than 1, and if they are real valued, then the system is stable or the signal is stable. Usually, when you have them, let's say, with complex values, they are conjugates. Just determine where the poles are, locate them at the unit circle. As long as it's less than 1 or within the unit circle, then the signal is stable. So in this case, our signal was stable. All right, some properties on the Z transform. So this one, we have done it a few minutes ago. When you have a summation of two signals, you take the summation of their Z transforms, and the region of convergence is the intersection between both the region of convergence, the first signal and the second one. An important property here, when you do shifting in time domain by a certain constant and not, then you just find the Z transform, but it's going to be scaled by Z to the power that shift. So if you have x of n that led to x of z, if you make this shift x of n, it's going to be x of z, z negative n, sorry, n minus n naught, n naught. To actually put it in practice, to have it as a proper example, if we have the signal here, and if we write it as it was, okay, let me have an example from just my mind, 1 over 5 to the power n u of n. So the data transform for this will be 1 over 5 over z minus 1 over 5. Well, 1 is going to be z over z. So this one is z. Over z minus 1 over 5. Now, let's say my example, 1 over 5 to the power n u of n minus 3. Or let's keep it simple, then we'll go to the complicated one later. If you face this example, you have 1 over 5 to the power n minus 3 times u of n minus 3. There are two ways to do it. You can say, okay, this is going to be equal 1 over 5 to the power n times 1 over 5 negative 3 times u of n minus 3. So take this one as a constant outside. Then you have this one and that one. Take it to the summation, do the tables, etc., etc. Or you can simply say, this is exactly as if I'm having 1 over 5 to the power n, u of n, but I made a shift by 3. Or you can assume that x of n equal 1 over 5 to the power n, u of n. Then x of n minus 3 equals what? 1 over 5 n minus 3 u of n minus 3, right? So I did shifting. Notice these two has to be the same. So we can call it a shift. N minus 3. I shifted all n by 3. So I know that 1 over 5 to the power n u of n will lead to z over z minus 1 over 5. Now, if I'm doing a shift by 3, basically, the z transform of x of n gave me x of z. Now, z the transform of x minus 3, the shifted version, gave me what? X of z times z to the negative 3. By using that property, you shift by a certain constant and not, you obtain the same transform, but you scale it with negative and not. So I'll go back here. I made the shift by 3. Then I multiply by z to the negative 3. Now, where is x of z? This is the expression. So here, this is the original one. Now 1 over 5 to the power n minus 3 times u of n minus 3 by applying z transform is going to be z over z minus 1 over 5 times z to the negative 3. Clear? Is it clear? So when you notice that there's a shift point for the original one, then you apply this property. Clear? Now, what if we have another example? 1 over 4 to the power n u of n minus 6. How are you going to solve this one? Any idea? And this is a good question that you may face in one of your exams. We said that as long as we have the shifts, we can apply that rule. I know that 1 over 4 to the power n u of n will lead to z over z minus 1 over 4, right? Yeah. But I have now shift by 6. But I don't have the shift in the exponent. So what to do? Do it this way. 1 over 4 to the power n times 1 over 4 to the power 6 times 1 over 4 to the power negative 6. Then u of n minus 6. Now, why I did this move? If you look at this one, what is the value? It's 1. It's as if you're multiplying by 1. It's 1 over 4 to the power 0. Now, what I will do, I'll take this one outside. So I have 1 over 4 to the power 6 out times 1 over 4 to the power n minus 6 u of n minus 6. صح? Do you get what I just did? I just multiplied by 1, but in a different form, and took one term outside of the multiplication. Then I will have n minus 6. Now my shift here and there, they are the same and scaled. So in this case, by doing the z transform, I will have 1 over 4 to the power 6 times. Now 1 over 4 n minus 6 u of n minus 6. So I will have the original transform z over z minus 1 over 4 times what? The amount of shift. And that's it. And then you can simplify 1 over 4 to the power 6, z negative 5 over z minus 1 over 4. Clear? Is it clear how I solve this one? All right. When you do scaling in time domain, you just have to scale the expression in the z domain. I don't usually prefer this one. Most of the example will be related to this one. Okay, time reversal, you just take the reciprocal of z. Upsampling, we'll talk about sampling next week, inshallah. So when you upsample, you scale the z. Mainly, we'll talk, like the focus will be on this one. And that's why you have an arrow there, actually. Pretty much like the Laplace and Fourier, convolution and time domain will lead into multiplication in the frequency domain. When you take the derivative, you are getting something like this. The derivatives in the z domain is a bit different than the continuous domain. So basically, you take the difference between two samples, and that's what we call a derivative. Accumulation is pretty much like integration. We have the zero value and the final value theorems. So x of 0 for any expression, just find the limit of x of z as z approaches infinity. Final value, and just evaluate this expression. We don't usually, again, deal with those. The widely used ones are this one and this one. Okay, some pairs, the delta function will lead to a 1. In fact, probably in all transforms, the transformation of the delta function will be 1. Unit step function is going to be z over z minus 1. And the region of convergence for all values of z larger than 1. The minus 1 u of minus u of n minus 1 will lead to the same. That's something we have seen last week in the Laplace. It's the same transform, but with a different region of convergence. Nu of n is basically z over z minus 1 squared. Similarly here, same transformation, but a different region of convergence. This is a widely used one. We'll use it also for the inverse, z transform. Z over z minus a will lead to a to the power n u of n, with a condition that a should be less than 1, and the region of convergence z is larger than a. Similarly, different region of convergence with the same transform. And yeah, the focus will be more into this one here and this one there. All right. So given x of n equals delta of n, find x of z. Let's say in the example, in the exam, I asked you prove that the z transform of delta of n equals to 1. So simply you go by the, so when you are given a question, prove that, you just immediately go to the definition. So here definition, n equal negative infinity to infinity, delta of n, z to the power negative n. So that is the x of z equal this expression. Now, what do we know about the delta function? It's only a pulse at n equals 0 and 0 elsewhere. So when you take the summation, you have zeros everywhere and you have only this pulse. So actually there's no summation. There's only one sample that has an amplitude of 1. That's going to be the answer. It's 1. Or you can say 0 plus 0 plus 0 plus 1 at center plus 0 plus 0 plus and so on. So that's negative 3, negative 2, negative 1 at 0, 1, 2, negative infinity, infinity, and so on. And that's it. So immediately you can say like this. Now for delta of n minus 1, we can use the properties there, or you can say I have shift by negative 1 to the by 1 to the right. So here I have at 1. And you can apply the expression 0, 0 plus 0 plus 0 plus 1 z to the power negative 1. 0 z to the negative 2 and so on. All right, or you can use this property. Now what about the unit step function? U of n is going to be summation n equal negative infinity to infinity u of n z to the power negative n. So it's going to be 0 to infinity. Unit step function will change the limit z to the negative n. And you refer to the ones here. And there you go. That's the one. So I have a equal negative z to the power negative 1. So it's going to be 1 over 1 minus z negative 1, or you can say z over z minus 1. And let's see the pairs are there for the unit step function z over z minus 1. Just go back by the definition. So finding the inverse is not trivial. It is solved by numerical analysis, or we can use a partial fraction expansion and use the Fourier pairs. So for example, if you were given this expression and you were asked to find the inverse of the transform. So the question will become like, okay, you have x of z, find x of n. And if you go back to the tables, none of the expressions there have an inverse directly for this one. But we can use partial fraction expansion to have it like a over 1 minus 1 over 4 z negative 1 plus b over 1 minus 1 3 z negative 1. And you can do cross multiplication. So I have a 1 minus 1 over 3 z negative 1 plus b times 1 minus 1 4 z negative 1. And this expression should equal to the numerator there. So I will have 3 minus 5 over 6 z negative 1 equals, and I rewrite that whole thing there, 1 minus 1 over 3 z negative 1 plus b 1 minus 1 4 z negative 1. All right. And by the way, here the expression was easily factorized, but expect something like a polynomial, z squared plus 3z plus 5, whatever. Now, what will be the best way to solve such a question? Substitute the values for z, right? No. You will make it complicated. Then you have a system of two linear equations, you substitute values, then you have
simplified then.
No, that's a waste of time and effort. The easiest way is you pick values of z that will terminate one coefficient. For example, what will be the value of z that will make this expression equal 0? So we'll start at z equal, I want to terminate this expression. A is a constant, unknown. And I have 1 minus 1 over 3z negative 1. That expression should equal to 0. Okay, so let's assume 3. 1 minus 1 over 3 times 3 to the negative 1, 1 over 3. 1 minus 1 over 3 times 1 over 3. So that's 1 over 9. So 3 is not the correct choice. See, when you see a negative power, immediately z is going to be that same value there. So add z equal 1 over 3. Why? Because 1 over 3 negative 1 equals 3. 3 times 3, 1. 1 minus 1, 0. So I will have a z equal 1 over 3. So I have 3 minus 5 over 6 times z negative 1. 1 over 3 to the negative 1 equals 3. So I have times 3. That equals to a 1 minus 1 over 3 times 3 plus b 1 minus 1 over 4 times 3. Again, z to the negative 1 is 1 over 3 to the negative 1. That is a 3. All right, so 3 minus 5 times 3 over 6. So we can simplify. That's going to be 2. That's a 1. 3 minus 5 over 2. 5 over 2 is 2.5. 3 minus 2.5, that is 1/2. So that's 1 over 2 equals. Now 1 minus 1 over 3 times 3, that is a 1. 1 minus 1, 0. So this term is gone. I will have b 1 minus 3 over 4. And that equals to what? 1 over t equals b times 1 over 4. So here b equals 2. All right, so B was the one associated with this exponent. Let's confirm before we proceed. So B is 2. There we go. It's there. Now let's find A. Similarly, at Z equal what? 1 over 4. I will have 3 minus 5 over 6 times 4 equal A 1 minus 1 over 3 times 4. B will become 0, right? Because that's the purpose of putting 1 over 4. So here I have 3, 2, 10 over 3. And I have this one. 3 is what? 15, sorry, 9 over 3. 9 over 3 minus 10 over 3, that's going to be negative 1 over 3. Just algebra, just make sure that you have it right. 5 times 2, that's 10 over 3. And I have 3, which is 9 over 3. 9 over 3 minus 10 over 3, that's negative 1 over 3 equals A. So I have 1 minus 1 4 over 3, negative 1 over 3. So I believe A should equal to 1. Let's go back to the slides. A equal 1. So we're on the right track. All right. So once we have these values of A and B, we can substitute them back to the original expression there. So here I have 1 over 1 minus 1 over 4 Z negative 1 plus 2 over 1 minus 1 over 3 Z negative 1. Now, if you go back to our tables, you probably will not find these expressions. Let me see. Yeah, there is no actually Z to the negative 1. So what will be the way to solve it? You multiply numerator and denominator by Z. So we'll go back here. So multiply by Z over Z and multiply by Z over Z. So I have Z over 1 minus 1 over 4. Sorry, Z minus 1 over 4 plus 2 over 2Z over Z minus 1 over 3. I believe this expression is found there. So I have step functions. No, in fact, not step functions, exponents with us. This is the one. Yeah, that's the one. So I Z over Z minus A. Z over Z minus A. Z over Z minus A. So the first one is 1 over 4 to the power n, u of n, plus 2, 1 over 3, n u of n. This is the final answer. Are we clear on this one? So make sure if you have a negative exponent for Z, you multiply the numerator and denominator by Z to get rid of that. Then you look for the proper expression from the tables. So I don't have it at just 1. I have as a function of A. So it's an exponent. So. All right. So here, so we've done this. Here is a complete solution. All right, so we are almost done with the lecture. System analysis. Basically, the block diagrams. So let's always assume that my input x of n, and I have the difference equation or the impulse response h of n, and I have the output as y of n. The relationship between them is convolution. So there you go, y of n equals x of n convolved with h of n. And in the z domain is their multiplication. So to find the response of the system, h of z equals y of z over x of z. Okay, system function, pretty much the same details as we did in the Laplace transform. So the LTI system is completely characterized by the system function. Yeah, it is always that the region of convergence includes the unit circle for causality. All right, so this is the block diagram we just applied. Nothing new from before, but we just changed the domain. Previously, we used Fourier, Laplace, and now it's the Z domain. When you have them in cascade or series, you just, in Z domain, you multiply them. And you can also, what they call it, interchange between them. If they are parallel, you just add them together. Now, stability, we talked about it. You look for the poles, and as long as the poles are inside the unit circle, then your system is stable. Okay, function includes the entire system. So here is another definition that the region of convergence includes the entire unit circle. So for example, here you have the region of convergence out of say the unit circle. So in this case, the system is not stable. This one is stable. Okay. So here consider you have this causal system as 1 over 1 minus a z to the negative 1. You multiply numerator and denominator by z to get it into the conventional form, z over z minus a, which is a to the power n, u of n. The poles here, the pole at a, and in this case, the region of convergence is outside the unit circle. In this case, so I have a pole at a, and the zeros at 0. So since the system is causal, and causality, I did not mention causality here. Yeah, causality, a system of the rational system, if all poles are inside the unit circle. So here it is assumed that since the system is causal, as mentioned here, then all poles are inside the unit circle. So in this case, it is stable. Okay, however, if this condition holds, it depends on the value of A. If A is larger than 1, then the system will not be stable in this case. Okay, in our case, I'll keep it more simple. Just find the poles, locate them. If they are inside the unit circle, then the system is stable. Invertibility is pretty basic. Find the function or the system that when you apply the Z transform to it, and let's say assume that you have x of z and you have h of z, and here you find another system h of negative z, for example, it will lead to the same input x of z. Okay, so that's what we mean by invertibility here. So h inverse equals 1 over h z. Okay, for differential equations, pretty much like what we did in Laplace. So here is an example. Now in differential equations, we don't use derivatives here because the derivative, if you remember, x prime of n, or the derivative is x of n minus x of n minus 1. Go back to the tables of properties. There's the one, differentiation. But actually, it's simpler than this. You don't have to worry about calling it the derivative. We know that if we do a shift, you are getting the transform, but you scale it by z to the power that shift. So if you go back there, so this is what we call a difference equation, and there are a lot of details in DSP, inshallah, when you take it in the future, the digital signal processing, if you are pursuing telecommunications or computer engineering. So in this case, the typical question would be, you are given this differential equation or difference equation. In discrete, we call it difference equation, and continuous differential equation. But anyways, you are given this difference equation, find the transfer function of the system. The transfer function, basically the h of z. and find its impulse response, h of n. So let's do that for this question here. So consider this linear time invariant system for which the input x of n and output y of n satisfy the linear constant coefficient difference equation. Again, difference equation, it has these delays. Now, the question is find x of z, because it's easier to find, then find the inverse. Not x of z, h of z. Then find the impulse response, h of n. Okay, so let's apply the Laplace transform for this. I have, the z transform. Z transform of y of n will be y of z. Z transform of y of n minus 1 will be y of z, z to the negative 1, and so on, x of z, and so on.
Does it not?
You mean this?
On the screen.
Okay, see, that's the thing. In discrete time, we have x of n, we have the square brackets. The z transform is continuous. So we don't have it like x of z. No. It's x of z. All right, so let's apply these concepts here. So I have y of z minus 1 over 2 y of z times z to the negative 1 equals x of z plus 1 over 3 x of z, z negative 1. As simple as that. Take y of z as a common factor. Have 1 minus 1 over 2 z negative 1 equal x of z as a common factor 1 plus 1 over 3 z negative 1. Now to find h of z, h of z equal y of z over x of z. So here is going to be 1 plus 1 over 3 z negative 1 over 1 minus 1 over 2 z negative 1. And that's it. Is it stable? Okay, poles. So 1 minus 1 over 2 z negative 1 should be equal to 0. That's the pole, right? Okay, so let's move this one there. 1 minus 1 over 2 equal z negative 1. Multiply by z for both cases. So z equal 1 over 2. Less than 1. So it is stable. I can go to the unit circle and the pole is there. All right, now what about its inverse Laplace transform? Any idea?
Multiply by z.
Before multiplying, let's break down this expression. So that's going to be equal 1 over 1 minus 1 over 2 z negative 1 plus 1 over 3 z negative 1 over 1 minus 1 over 2 z negative 1. So it's like having a over b over c. It's going to be o over c plus b over c. Denominator, you can distribute it over the numerator. So, all right. Again, we are not used to find this z to the negative 1. So for the first expression here, so times z over z. So I have z over z minus 1 over 2 plus 1 over 3 over z minus 1 over 2. So this one easily 1 over 2 to the power n u of n. What about this one?
Tables.
Check the tables. Let's hope you have something like that. And if not, we will force it to be something like that. So do we have a case where you have a constant over z minus something? Let me see if we can remove all these. All right. Do we see any constant over something like that? No. How to solve it? This one.
A z over z minus a square.
Where?
In the table, I mean.
This one?
To one of them.
This or this one?
9.
9? You're complicating things. Or 8. 8 and 9 are the same. You're making things complicated. There's an easier way. Let's assume we were already there. So we're already at the, I did the opposite. So if I divided by what? By z, you mean? This one is, you cannot, it's not divisible. You cannot distribute this one into, cannot distribute the denominator on the, to the numerator. Is that what you mean? Like partial fraction expansion? What will be the other term? See, partial fraction expansion, you just break down the denominator. Let's try this. Let's try you multiply by z and z negative 1. It's multiplication by 1, huh? Now, if I have this 1 over 3 z over z minus 1 over 2, so this one is easily plus 1 over 3 1 over 2 to the power n u of n. Right? Now I'm left with an issue that this one there. What will be the case when I multiply by a z to the power negative something? Let's go back to the tables. And not this one, this one. Where is the case where I multiply by a z to the power negative something? Which is the number? Translation. Or basically, when you do a delay or a shift in time domain. So in this case, this is my x of z. So that's my x of z. And corresponding to x of z is this x of n. So x of n 1 over 3 times 1 over 2 to the power n u of n. That is x of n. And this is x of z. Now I'm weighting x of z by z to the negative 1 means what? I'm doing what? I'm doing a shift by how much? By 1. So basically, n minus 1 minus 1. And that's it. When you multiply by z negative 1. Is it clear? Is it clear what I did there? Okay. So in this case, we made a comment that it is stable, and we found the system response, etc. So there is only one pole at 1 over 2. There's 1 0 at negative 3. And it is stable. And we found x of n, which was, I don't think it was required. All right, now another question. Find, for this difference equation, find the impulse response h of n. Even though I did not say that find h of z, you have to find it. There's no way to find h of n directly. So find h of z, then do the inverse transform. Pretty much similar to the previous example. So here, find h of z first. So I have y of z minus y of z, z to the negative 1, equals x of z. Take y of z as a common factor, and you have 1 over 1 minus half z negative 1, z over z minus 1 over 2, and that's a to the power, 1 over 2 to the power n u of n from the tables. Another important thing about difference equations that they could be represented by a block diagram. And the elements for the block diagram, we have an adder and we have a delay unit. That's how we symbolize a delay unit. Because see, y of n minus 1 at the transformation, it's z to the negative 1. And we have the node and so on. So how to represent this difference equation as a block diagram? Basically, I have x of n, and I have y of n, and I have my adder somewhere there. Now the output, and always you start by x of n, and you finish by y of n. And there is also another component, which is a multiplier, a buffer, like a multiply by a certain coefficient or constant. So in this example, rearrange the terms in a way that you have it like y of n equals whatever the other expressions. So this one here, we can rewrite it as y of n equal x of n plus 1 over 2 y of n minus 1. Tamam? All right, so I have y of n equals x of n plus, this is the summation, a shifted version of y of n. So I have y of n here. I will make a delay. What was the block for the delay? Z negative 1. So in this case, I have what? Y of n minus 1. Then it is scaled by 1 over 2. And it's going to be the input for the adder. So this is the block diagram of this difference equation system that I have. Clear? Yeah, you may have a question like this. So that's same example, but with different difference equation. So this is how you represented the block diagram. Another question, we probably try this one here as a block diagram. So take this one there. So I have y of n equals x of n plus 1 over 3 x of n minus 1 plus 1 over 2 y of n minus 1. So here I have x of n, I have y of n, I have the other at the middle. So I have x of n immediately going there. Okay, y of n, there's no scaling. Then I have 1 over 3 x of n minus 1. So I'll make a delay. So in this case, I will have x of n minus 1. Scale it by how much? 1 over 3. That's the first part. So I'm done with x of n. I'm done with 1 over 3 x of n minus 1. I will have 1 over 2 x y of n minus 1. Again, we have a delay. In this case, it's going to be y of n minus 1. Scale by 1 over 2. Then that's going to be your other input there. So this is the block diagram of this difference equation. Again, in discrete domain, we don't call it differential equation. We call it difference equation. In continuous domain, we call it differential equation. Okay. Another example here, and we'll finish the lecture at this point. So consider the second order system function here. Now, by the way, we did not talk about orders yet. We'll more about it in DSP. The orders is basically the maximum power of Z. So in this case, when you distribute the multiplication, you'll have -2 or 2, it doesn't matter. So you have the highest power is at 2, so that's the second order. If the highest power is 3, that's the third order. If there is only just Z, that's the first order. So in this case, you have this system, and if I ask you draw the block diagram, and let's assume this expression was not there. Assume this one was the only expression given to you. You have to distribute the multiplication, have it something like this, and you should know that h of z equals y of z over x of z. Then you multiply. So you have y of z by 1 plus 1 over 4 z negative 1 minus 1 over 8 z negative 2. That's equal to x of z. Distribute y of z plus 1 over 4 z negative 1 y of z minus 1 over 8 z negative 2 y of z equal x of z. Now find the difference equation. I go back to the n domain, to the discrete domain. Y of z will give me y of n. 1 over 4 z negative 1 y of z, so that's a delay by 1. So 1 plus 1 over 4 y of n minus 1. Is it clear how I got from this one to this one? Minus 1 over 8 y of n minus 2 equal x of n. Now take this one and that one there. So I will have y of n equal x of n minus 1 over 4 y of n minus 1 plus 1 over 8 y of n minus 2. So to draw the block diagram, I have x of n, I have y of n, I have the adder here. Okay, so x of n, immediately it goes there, it's not scaled or weighted, plus or minus 1 over 4 y of n minus 1. So I'm gonna create a delayed version of y, z negative 1. So in this case, I have, let's not write it this way. So that is y of n minus 1. I will scale it by -1 over 4. Then you put it at the adder. Now there is another delay because I have another delayed version here. Now notice here, I have y of n minus 1, z negative 1, that's a delay by an extra unit. So you don't have to do z negative 2. You cannot do that. It's only a single block, a single delay unit. So I have the first delay unit, got y of n minus 1, delay it one more time. So in this case, we have y of n minus 2, scale it by 1 over 8, and you put it at the summation. And that's going to be the final answer in this question, the block diagram for this difference equation. Okay, you can have another summer here or can immediately put it at that other point here. And that's it for this lecture. Okay, more record, stop the recording. ما تحقق